go. Yes. So the recording has started. Exam 3 review session starts now and there. So now you can see the entire screen, I'm assuming. And so would one person maybe give me the go ahead that everyone's seeing exactly what you're seeing the first problem, right? And I need to move this away.
It looks clear to me.
Looks good to you? All right.
Yeah, that looks good.
Okay, good. Thank you very much. So let's get started. So the first problem in the exam was about this particle of mass 1 kilogram moving along the x-axis. There it is, subjected to a contact force, which is shown in the figure. It goes from 0 up to a certain value and back down. And as a consequence of this force, the particle that feels the force, it speeds up from 3 meters per second to 7 meters per second. And they've told us the locations for these speeds. And so the question is find the value of F max. And one thing about exam 3, I suppose, is, and in general, I suppose in physics, is that wherever you can use the principle of conservation of energy, use it, because it's a simple enough principle, doesn't have any vectors, only scalar quantities. Um, and in this case, the application of the force speeded the object up. And of course, what the force did was it did work on the object, and that work showed up as an increase in kinetic energy. So this is a good place to apply conservation of energy. And whenever we say conservation of energy, in this course we mean conservation of mechanical energy, which is, and let me get my glasses on here. All right. So it's always change in kinetic energy plus change in potential energy equals the work done by non-conservative forces, right? And the only forces that are conservative are the elastic, the gravitational forces, and I don't think that in this course we have learned of any other conservative forces. Um, in 192 you learn of electric and magnetic forces, and they are conservative forces as well. But all other forces are non-conservative forces. Any kind of contact force, tension force, friction force, they're all non-conservative forces. So they all come in. So in this case, I mean, it's a contact force. So it's a non-conservative force. And and of course, the kinetic energy changed. So this guy is, there's a Ke final um, minus a Ke initial. That's the change, right, in the kinetic energy. And meanwhile, the change in potential energy, well, it's moving along x. There is no mention of it changing its height or anything. So this is not relevant, all right? So the change in kinetic energy is the work done by the non-conservative force. And the work done by the non-conservative force, is the integral of the force, uh, the f dot dx, and it's all one dimension. So f dx integral, which is basically, so this is the area under the fx curve, right? X is the displacement, I mean the location, so the change in location, that's your displacement. So that's just the area under the fx curve. And so I guess we've set up the problem at this point. We want to find the value of f max. And so you see that's going to show up in this part of the equation. So what's the Ke final minus Ke initial? Well, it's 1/2 the mass, which is 1, and then v squared, right? And so v final squared, I mean, this is basically 1/2 mv final squared minus m/2 v initial squared, right? So I pull out the 1/2 times mass common, and then the v final squared is 7 squared, and the v, that's 7, and the v initial is 3 squared, okay? And this is the area under the curve, and the area under the curve, well, it's just, this triangle. So that's just 1/2 times the base times the height, which is F max. Yeah. So I solve for this, and the half cancels on both sides. 49 minus 9, that's 40 divided by 2. So F max equals 20 newton, right? So that's this answer. So that's how we get that answer, 20 newton. Okay, so after every problem, I'll just ask you quickly, are there any questions at all about this? Is everyone good? And I'll give you like 5-10 seconds, and then we can. One thing I noticed about this exam is that there are some difficult questions up front, and then there are a lot of easy questions in the middle. So I guess it's a good idea to just quickly look over the questions before you decide. I mean, you select the ones that you think are the easiest to do first. Okay, so that's the first one. And then let's look at the next one. Number 2. So number 2 is actually another conservation of energy problem. You have this block that is pressed up against a spring, okay? And they've given you how much the compression is. They've given you the force constant for the spring. And then this block is launched, and it climbs up this frictionless surface, and then it launches off here, and it follows the shape of a projectile, trajectory, the parabola. And so this launching off, it's going to launch off like that. Let's say that this velocity is v launch, okay? And you can see that this angle of launch would be the same as this 45 degree here, okay? All right. So basically we're supposed to find out, how much did it, as it launched out, how far did it go? What's that d value over there? So, so we want to apply conservation of energy, and if you knew the launch velocity, then finding out the rest, I mean, that's not a problem at all. It's just a simple projectile problem from here on. So all I need to do is, use conservation of mechanical energy to find the launch velocity, right? And then after that, just projectile motion. Yeah, so that's all that we need to do. So let's apply conservation of mechanical energy. And whenever we do that, we did this in the previous question too, but maybe didn't emphasize it. Whenever you want to apply a conservation law, like mechanical energy or linear momentum or angular momentum, there's always an initial and a final. So in this case, there's the initial position is here, and the final position is right here when it launches. Okay? You don't need to look at anything in between, because there's no need to, it's all frictionless, and So I can look at those initial and final points. And the law is always change in kinetic plus change in potential equals the work done by the non-conservative forces, right? So in this case, there are no non-conservative forces. The most common non-conservative forces are friction, tension could be a non-conservative force, or you might have someone pushing or pulling, and those are non-conservative forces. In this case, there's only the spring force, and there's gravity as it climbs up, right? So there is no non-conservative forces, so that's 0. And the change in kinetic energy, well, it's always 1/2 mv final squared minus 1/2 mv initial squared, but it starts from rest, right? It's pressed up against the spring, so that's 0. And of course, this is, well, I'll put in the mass. The mass is given to us to be 200 grams. So that's 0.2 kilograms, right? There's the mass. And the V final is the V launch squared, right? And we want to find this out. Okay, and then what about the potential energy? Well, this, the change in potential energy, well, there are two kinds of potential energy in this problem, and that's always the case when you have a spring in the problem. You have a potential energy spring, right? Let's just say spring, plus there is the potential energy gravitational, right? Actually, let's just say elastic. I don't think I've been using, okay, elastic. Okay. So what's the change in potential energy elastic? Well, in the beginning you had potential energy, and in the end you did not, right? Elastic potential energy. There's no spring at the end. So the final elastic potential energy is 0, and the initial elastic potential energy is 1/2 kx squared, right? And k, right, I'll just remind you that PE elastic is 1/2 kx squared, okay? And PE gravitational, the change is mgh, right? So anyway, so and h is the height by which you elevated yourself. So there's the height, 2 meters. Anyway, so for the elastic, you have the final minus the initial, so that's 1/2, and k is the force constant, 1400 Newton per meter, and then the compression, x squared, right? That's the amount the spring was compressed or extended, okay? So it's not the length of the spring, it's the compression or the extension of the spring. And they've told you that the compression is 15 centimeters, so that's 0.15 meters squared. So this is your change in elastic energy, and then the change in gravitational, it went from this height here to that height there, and the difference is 2 meters. So it's mgh, and the mass is, we just said, 0.2 kg. G is 9.8 meters per second squared, and h is the height, which is 2. All right, so we have all the things together, and we can solve for V sub L, because 1/2 0.2 V sub L squared, so that's your change in kinetic energy. Change in potential is, there's first this minus 1/2 1400.15 squared, and that's your elastic change in potential energy, change in elastic potential energy, I mean. And then there is the change in gravitational, which is right there, 0.2, 9.8 times 2, and all of this, change in kinetic plus change in potential, is equal to 0. Okay, so we solve for V sub L, right? And what we find is that V sub L, I have it worked out here, V sub L works out to 10.88 meters per second. Now, one thing, a quick thing, and this is maybe obvious, but for example, here you see all the answers are to the first place of decimal, right? So you look at the answer, and if it's to the first place of decimal, then while you do all these calculations, always work it out to the second place at least. There's no need to go out till the fourth or fifth, just one extra, right? So the second place, and we'll keep that, and then we'll round it off at the end. So I'm not rounding this off to 10.9 just yet. I'm going to keep the 10.888. Okay. So when we do this, then you see we've done this part that we were saying. And once we know this, then the launch velocity, now it's just projectile motion. So we can do that now. So projectile motion. So here's a quick, I guess, a quick recap that you have something going out like this. V launch equals 10.88 meters per second. It does this number, right? And this angle is 45 degrees, and we're supposed to find out the horizontal range. And so how do you look at projectiles? You always look at the horizontal motion and the vertical motion, right? Separately. Horizontally, all you're applying is that formula, what is it? The delta x equals v initial in the x, delta t plus 1/2 acceleration x, delta t squared. And of course, you can also have the y, right? So if I apply this in the horizontal direction, then d is the distance I moved out horizontally. The v initial in the x direction is 10.88 cosine 45, right? That's right here, right? That's the cosine. And so vi sub x. And then delta t, I don't know what delta t is, but once I know it, once I know delta t, I will know what d is. And that's what I want to find. But where would I find delta t from? Well, I will get it from the vertical direction. And in the vertical direction, here's your v initial, right? And this is 10.88 sine 45. Okay, and this was 10.88 cosine 45. All right, and so in the vertical direction, what's your change in, change in position in the vertical direction? Well, you started from 0 and you came back to 0. So 0. And what's your initial velocity in the x direction? Well, we just said 10.88 sine 45 delta t, right? Plus, and in kinematics, I always like to indicate what my positive directions are. So I always draw this in. I mean, you could have chosen any direction to be positive, but I like to indicate that when I work problems out, just so that it's clear. So in this case, in the vertical direction, you got this, and delta t plus 1/2. The acceleration is minus 9.8, right? Because it's down. And then delta t squared. And you'll notice that in this equation, delta t is the only unknown. I can solve for it, right? So 10.88 sine 45 delta t is equal to 1/2 9.8 delta t squared. So one of these delta t's cancels, right? I'm just solving for delta t here. And so now I have from here delta t is, I solve for it, 2 times 10.88 sine 45 divided by 9.8. And delta t works out to 1.57 seconds. So once I have the time of flight for this object, then I just take this and plonk it in here. Plonk. Okay, and when I do that, I get d. Okay, I get that d equals 12.1 meters, which is this solution. All right, so any questions on this one? Is this good? We're doing good?
All right. Yeah, looks good.
All right, good. Thank you. Thank you very much. So I suppose then let's go to the next one. Number 3. Here's number 3. And this one again, I mean, in fact, almost as a default, anytime you look at a problem and if you're thinking, where do I begin? Like, it's okay to have the thought cross your mind that, can I use conservation of energy? And that's the first thing. Even in real life, like, I mean, when you're solving physics-related issues, it's always, can I use conservation of energy to get by? And then you think about forces and vectors and things like that later. So in this case, once again, it's a clear conservation of energy problem because there's a initial, which is the situation shown here. So let's just call this, initial. This is like the initial position. And then the final is where this block hits the ground. It's about to hit the ground. So it's about to hit the ground. So it's still traveling, right? I mean, that's why they're saying, what's the speed just before hitting the floor? So just before hitting the floor, that's the final position. And if this dropped by 17 meters, then this must have traveled along the incline by 17 meters, right? So it's here now. So it moved forward by 17 meters, right? So this is the final position for that. Okay, and I guess actually our diagram is all set to go. We've got our initial and final positions marked. So change in kinetic, change in potential, work done by non-conservative forces. And the thing to understand here is that, yes, there are non-conservative forces, oh, and there's friction. So there's friction between this. So right here, there is friction, and the mu sub k is 0.2. Okay, so so the non-conservative forces, let's just look at this for a moment. Non-conservative forces, there are two forces. There's friction, and there's also tension. But we're considering the system to be the two-block system. We're not looking at one block alone by itself and then another block by itself. We're not considering them separately. We're looking at the entire system. So the tension force is actually are an internal force. They cancel each other out. I mean, there's tension pulling up on this, and then there's tension also acting on this, and both those tension forces are acting, upward, and they're canceling each other out. So for the whole system, the two-block system, so I'm just going to write that here, that for the two-block system, right, our system consists of both the blocks. Tension forces cancel out. They're internal forces. They're like an action-reaction thing. They cancel each other out. Okay? And so the only force that you have to then consider is the frictional force that acts on the system. That's an external force. So that's an important thing. These are non-conservative external forces to the system. Okay? So external. The tension is an internal force. Okay? These are internal to the system. All right? And just holler if you have any doubts or anything anywhere. All right. So okay. So now we can look at this, and we've got our equation set up. So what's the change in kinetic energy? Well, in the final situation, you have the 1/2 and whatever velocity this guy has, right? Say v, and that's what we have to find out. Well, this guy will have the same velocity, right? It's moving at the same velocity because the string doesn't bunch up or stretch or anything. It's a, so both have to be traveling at the same velocity. So this is the final kinetic energy is 1/2 times the mass times v squared plus 1/2 times the other mass, 47 times v squared. And the initial, because of course this is Ke final minus Ke initial, and the initial kinetic energy is 0, right? Because both the blocks were at rest. What about the change in potential energy? So change in potential energy for this block, the 110, it fell by 17 meters, so it lost potential energy. The negative sign expresses that, and it's mgh. So 110 times 9.8 times 17, and that's the potential energy lost by the 110. Meanwhile, the 47 gained potential energy. It rose by a certain height, right? How much height did it rise by? Well, if we're looking at the front edge, so the front edge rose by 17 meters, right? And rose by 17 meters along the incline, so the vertical height is what we care about. So this is the height that it gained, right? And so this height, and of course, so there's the hypotenuse, 17, and this angle we know is 30 degrees. Okay, so the height is clearly 17, the hypotenuse sine of 30, right? So it gained in potential energy, so plus 47 is the mass, 9.8 is the little g, and then the height gained is 17 sine 30. Okay, so we got that, and the change in kinetic, change in potential, and now what's left is this work done by the non-conservative force. So let me pull that out here. Okay, so work done by non-conservative force, there's only the friction, and of course friction, so let's just look at that. So here's the incline, here's the block, okay, 47 kg block, and as it's moving in this direction, there's a frictional force acting on it, And this frictional force, so the work done by the non-conservative force is simply friction, let's call it F, and then, it moved by a distance d, okay? So it's just force times distance d. They're in opposite directions. The displacement is up, right? The displacement is up. The force is in the other direction, so it's F dot d, right? You get a cosine of 180 degrees, and so it's a negative work. Okay, and this we can calculate out to be, now what's the frictional force? The frictional force is always mu sub k times the normal force, right? And the normal force from your free body diagram, there's the normal force from the ground on the block, and this is in reaction to, and at this point I think everyone is very comfortable with all these things that I'm doing here, that there's the weight mg, right, which resolves into a component this way, which is mg sine of this angle theta, and a component like that, which is mg cosine theta. And this mg cosine theta is the force with which it presses into the incline. So that's the normal force. The normal force must equal that, right, for the block to not fall into the incline or lift off the incline. So therefore this is mu sub k times mg cosine theta. That's your frictional force. Okay, so so this work done by the non-conservative force is minus mu k mg cosine theta times the displacement d. So let's put in the values now. So this is minus mu sub k is what, 0.2. The mass is 47. The g is 9.8. Cosine 30 degrees, and then the displacement is 17 meters. So I have now all the components I need for this equation. Here's the change in kinetic energy, which has the V that I'm after. Here's the change in potential energy, which is just numbers. Here's the work done by the non-conservative force. I'm sorry, I sometimes write this uppercase, sometimes lowercase. That's just me being loose. All right, and then so now I go ahead and equate it all. I just put it together, right? So 1/2 110 plus 47b squared minus 110 9.817 plus 47 9.817 sine 30 equals minus 0.2 47 9.8 cosine 30 degrees and 17 multiplied by 17 also. So all of this is in there, and then I solve for V and I find V is equal to, don't forget to take the square root, 12.9 meters per second. Okay, and so that's the 13. All right. You know for a fact that on the final there will be a conservation of energy problem. So the ones that we have been doing, I mean, one of these is going to be on there. So hopefully you feel very comfortable with the concept. So any questions? So let's look at our pace here. I mean, these are the numerical problems, so they're taking more time. So about 40 minutes, 38 minutes in, we've done 3. Yeah, cool. It seems like a long problem when I drone on about it, but when you're actually in an exam situation and doing, you can get through it pretty quickly. Okay, so no questions? All right. No? Yeah. Okay. So remove this then. Move on to the next one. Going. And now we go on to the next one here. This is a nice conceptual one, short one. I hope you can. That's too small, isn't it? Okay, so I'll just read it out. A crane lowers a steel girder. So here's your steel girder, and there's a crane that's, you know, attached to it. I mean, it's got a rope attached to it. And so this crane is lowering the steel girder gradually into place, and it moves at constant speed. Okay, so consider the work done by gravity. So on this steel girder, there's the force of gravity, right? And so it's talking about the work done by gravity uh, and the work done by the tension. So there's the tension force, right? And so work done by tension. So we have to consider them. So we consider them. That's the considering pose. You put uh, you put your fingers below your chin and you consider. So which of the following is correct? So several choices. And it seems I read the choices and they're talking about, you know, negative. Which of these works is negative? Which is positive? Are they both zero? Well, they're not zero because there is a force and there is a displacement in the direction of this force, opposite to the direction of that force. So, as long as there's a force and there's a displacement, the work is not cannot be zero. So, I mean that can be true. Uh, but then it's all about, oh, and look at that. There's two of them that have the same choice. So that's kind of weird. But other than that, it's just the sign of the work is what they're asking about. So this is easy. I mean, the work is always the force dot the displacement, right? And so this is force times displacement times cosine of the angle between them. So clearly, if the force is in the direction of the force, then the theta is zero, and this whole thing is positive. So clearly, gravity is positive, right? The work done by gravity is positive because if you're lowering the girder, so work done is positive. But the work done by tension is negative because the theta is 180 degrees. So the force is wanting to pull it up, but it's going down. So the work done is negative. So the work done by gravity is positive, and work done by the tension is negative for the wind there. Okay, is this cool? That was not bad. Yeah, all right. So, and you know, by the way, if uh, after we're done or at some point or like later or whenever, I mean, if you have any questions at all about the course, I mean, feel free to. You don't have to always contact your own section instructor. You can contact me, and I'll be happy to answer any questions. Um, contact whoever, you know. Um, let's see if we have some time left at the end, and we can. I'd be happy to take questions from the course, from anything. Okay, so let's look at number 5. This also is an easy one in the sense that nothing, no math to do. Now, again, this may be kind of small to read. So let me just take a quick. So, Dhruv, can you read this on the top?
No, not really.
Okay.
It's really blurry.
Yeah, and I can't. I don't have a zoom thing on this, so I'll read it out. It's a pendulum swinging back and forth. That's what the first sentence says. Swinging back and forth is shown. The mass of the string is negligible, so forget that. All the mass is in this bob. And the forces acting on the pendulum. So, what are the forces acting on this pendulum? They're the weight of the pendulum. So, let's say, so there's the weight, right? W. And then there's the tension in the string, which always, of course, it's like that. And then there's air resistance. So air resistance, I mean, so as it moves in this trajectory, everywhere the air resistance is opposite, right? So I mean here, and it's tangential. So it's just gonna like, you know, like that. So that's your air resistance, F resistance, okay? All right, so now the question that they're asking is that which of these forces does no work on the bob as it moves from A to B? So we just said that the work done is force dot displacement, and which means the magnitude of the force, the magnitude of the displacement, cosine theta. That's the important thing. So you can clearly see that, for the resistance, let's air resistance, the theta is 0. So yeah, the air resistance is always doing work, and it always does negative work, by the way, right? Because it's the bob always moves, like whatever direction the bob moves, the resistance is in the other direction. So air resistance, the work done by the air resistance is always negative. What about the weight? Well, the weight is a little tricky because there is the displacement as it moves in this direction, right? So let's say as it moves in this direction, you'll notice that there is an angle theta between them, between the motion, the displacement, and so there is a work done, and it is when it's traveling downward, the work done is positive. When the bob is traveling up, then the work done is negative, right? So when traveling down, I'm clearly overanalyzing the question, um, but I'm a professor. Well, what else will I do? It's a physics question. Physics professor, you let me loose on the so getting to take the exam myself here. So after 30 years of setting such exams, I think I've gotten pretty good at taking these exams. So, uh, positive when traveling down, negative when the bob's traveling up. All right, and but I left the culprit for the last one. You'll notice that the tension is always at right angles, everywhere at right angles. Okay, so theta is 90 degrees, and of course that means that the work done, cosine 90 is 0, so there's your culprit right there. So the answer is the tension, okay, everywhere. There's no work done by the tension. Sometimes, just to give you a quick, sometimes the normal force also happens a lot, that, something is moving along, and you'll notice that the normal force is always at right angles. And no matter what kind of surface, you can draw any kind of god awful surface you want, and everywhere as the object is sliding along, the normal force is always at right angles. Okay, so so the work done by the normal force is usually 0. Not always, but it usually is. Okay, any questions? We good? Then let me move on to the next. And so now I think we're going to move away from, I mean, it might still crop up every now and then because we're always wanting to use it, but we're moving away from conservation of mechanical energy, and we're now facing another conservation principle. So conservation of mechanical energy works fine as long as there's nothing colliding with another particle or another object. But the moment you have two particles interacting, 2 or 3, well, then you have to talk conservation of linear momentum. In this case, it's not angular momentum because nothing's rotating. So that's what we're up against this one. Now in this case, there's a bullet coming along, hitting this block. It's just like that air cannon thing that we did. The ping pong ball came, hit the can, and then they both kind of, fell over. And of course, this is all projectile motion. So, so our plan, we want to find the initial speed, right? So this is what we want to know. the initial speed. And so what our plan is that we've been given how far out it went. So from this distance, so our plan is that from the projectile motion, because we know quite a bit about the projectile motion, you see, we know that this is 1 meter, so we know the height and we know the horizontal distance. So that's actually quite a lot of information. From the projectile motion, we can find the launch velocity here. And then from the launch velocity, using the conservation of linear momentum, we can find the initial velocity. Okay, so that's the plan. All right, so for the projectile motion, once again, there's horizontal, there's vertical. It's always the same thing. And the equation I always end up using is, again, delta x equals vx initial delta t plus 1/2 acceleration in that direction, and this. That's the formula I always end up using. So in the horizontal direction, the delta x, so we're starting at this point, and there we are on the, so this is after the collision, right? So this is the bullet plus the block after the collision. They're traveling together. The horizontal distance is 2. That's 2. The initial velocity is the launch velocity, and the time of flight is delta t. I don't know delta t, but I will find delta t from the vertical motion, and once I know delta t, I will know the launch velocity, right? So vertical, what about the vertical? And like I was saying, always indicate your positive directions. So this positive x and up is positive. Okay. So what about the motion in the vertical direction? I fell by 1 meter, so that's a -1 is my delta y. The velocity in the y direction initially is 0 because it's all horizontal. The acceleration is minus 9.8 because up is positive. I just always do that. And the delta t squared, of course, is the unknown. So from here I can solve for delta t. Don't forget to take the square root, and it works out to 0.45 seconds. Okay. So this then I take and plonk into this equation, and I find V sub L works out to 4.43 meters per second. So my first step here is done. Now I need to do this step here. So I need to apply conservation. So, the situation is that whenever I apply conservation laws, I need an initial situation. The initial situation is bullet coming, block sitting, that's the velocity. This is 4 kg, 8 grams. 8 grams is 8 times 10 to the minus 3 kilograms. Okay, so so that's your initial, and then the final is that the block has been sort of semi-destroyed by the bullet. So it's an inelastic collision. It burrows in, is what I'm trying to show. And then they both travel with the velocity v launch, right? So this is just before they. There's no table here. There's no surface. It's about to go off. Okay. So there you go. So now between the initial and final, so what is it now? The initial momentum equals the final momentum, right? and initial momentum is 8 times 10 to the minus 3. It's all in the bullet, okay, and nothing in the block. But then in the final, they're both together, so it's 8 times 10 minus 3 plus the 4 kg, right? And the final is the V launch, which we know is 4.43 meter per second. So everything's known, and we can find out V from this, okay? So when we solve for V, it works out to, this is 0.008, so that's 4.008, 4.43 divided by 0.008. And so you see, because the mass of the bullet is so much smaller, you end up with a pretty large velocity, 2216.8 meter per second, which of course is 2.2 kilometer per second. And so there's the answer for that. Okay. Any questions about that one? Everyone with me? Okay. So, yeah. Okay, thank you. So, there. Now let's look at, setting these exams is fun. Taking them, not so much. I'm kind of exhausted already. And then I've just been through the first 6 here. So my full sympathies and understanding to all of you who have to take these 2-hour exams. I'm so glad I don't have to take them anymore. It's good on the other side when you're setting them. Okay, so now we have this conservation of linear momentum problem, because it's collisions. The moment things collide, it's going to be a conservation of linear momentum problem. And in this case, again, so there has to be an initial and there has to be a final, right? Because I got P sub I equals P sub F. It's a two-dimensional collision is what it is. So in the beginning, you have this guy going along in his truck, and it's 2100 kg, and it's 2 meters per second. And for the sake of making an interesting two-dimensional linear momentum problem for us, he goes and gets bammed into, not only from the below by this 4 meters per second, 1200 kg car, but also he gets rear-ended, 1500 kg, traveling at 10 meters per second. So it makes for an interesting collision. It's very rare to have that kind of luck, but you get hit on both sides. And so the final situation is that and then everyone gets all entangled, and everyone kind of, you can see that because of the way this collision is set up, everything's going to kind of go off like that, right? And it's just one big tortured mess. And it's so the question is that, what's the velocity at which it's going, and then the I guess they don't really want the velocity, they want this angle, theta. And it's all north of east, north of east, north of east, so north of east. So they want the angle theta. All right. So what we do then is we apply conservation of linear momentum in the x direction and also in the y direction, right? So because it applies in both directions, each component is conserved. So let's look at the first one. So in the horizontal direction, right? You have your initial momentum, 1500 kg guy, tearing in with 10 meters per second, positive, this is your positive direction, these are the positive directions. And you also have the 2100 kg guy moving at 2 meters per second. So that's your initial. Now this guy, the guy is moving straight up north, he has no horizontal component, right? So there you go. And this is the final, equal to the final. Now the final, of course, they're all bent out of shape, but the mass stays the same. Okay, and the velocity in the x direction, you can see is, v cosine theta, and they're all moving together with the same, so v cosine theta. Okay, and so you can see from here that therefore v cosine theta is equal to all of this divided by that, which is 19200 divided by 4800, that's 4. Okay, so we got that. There are two variables, so I need one more equation, two equations, same number of equations as variables, then I know I can solve it. And so now, of course, the vertical direction. And the vertical direction, things are simpler. There's only one guy with a vertical momentum, that's the 1200 times 4. So that's your initial momentum. Final momentum, they're all traveling together, which is, all of this is 4800. Okay, and of course, v sine theta, right? So there's the v, so there's v sine theta. Okay, so v sine theta. So this tells me v sine theta equals 1200 times 4 is 4800. So anyway, so that's 1. So now I have two equations, v sine theta and v cosine theta equals 4. And the standard way to solve this, if you're going after theta, you want to get rid of the v. And it's the standard thing, solve for one from the other, solve for one, substitute in the other. Or you just divide one equation by the other equation. The v goes away, tangent theta is 1/4. And so this tells me theta is tangent inverse of 1/4, and that's 14 degrees. So this is equal to 14 degrees. And so it's one of the choices right there. Okay. If they had said that, tell us v instead of theta, then, well, once you know theta, you can, of course, back out what v is. This good? Any questions here? Yeah, and if we pass a problem by and you discover you have a question on it later, just speak up, not a problem at all. Okay, so there. Number 8, that's a conceptual one. This too is a momentum problem. So basically in this, they're saying a rubber ball and a clay ball are thrown at a wall with equal speeds, right? So rubber ball and then clay ball and equal speeds. The rubber ball bounces, right? So it comes back with some speed, let's say v prime. And the clay ball just goes poof, just sticks there. Okay. So which ball exerts a larger impulse? And so if you look at the definition for impulse, impulse is, it comes out from, you know what the second law is, right? The Newton's second law is force equals rate of change of momentum. And so that means that F dt equals change in momentum. Like, I mean, if you do the integral of the force dt, then that gives you the change in momentum, right? And this, of course, is the impulse. That's by definition. So it's kind of a force multiplied by the time over which the force acted, right? I mean, so when, the ball hits the wall, it deforms a little bit, then comes back out. You know how a rubber ball deforms, squishes, and then bounces back out. So all of that's taken care of by the impulse, the force multiplied by the time. And so this impulse is the change in momentum, right? So this change in momentum is mv final minus mv initial, right? And so you'll notice that if you rebound, then if you said that, let's say this is the positive direction, then you notice that for the rubber ball, the change in momentum is m, and the final momentum is to the left mv prime, so it's negative, right? Minus, and the initial momentum is mv going to the right. So you see that the change in momentum is minus 2, I'm sorry, it's minus mv plus v prime. Yeah? So the magnitude of the change in momentum is equal to the magnitude of that, and you see how these two added together. On the other hand, if you look at the clay, then the change in momentum, well, the final momentum is 0 because it just got stuck there, and the initial was mv, so initial minus final, final minus initial, right? And so this is mv. So you see how the clay is always less than the change in momentum for the rubber ball. So because the rubber ball bounced back, it has a larger change in momentum, which means it has a larger, the impulse is larger. The impulse from the wall on the ball and from the ball on the wall. Wall on ball, ball on wall. The impulse is the same on each other. Okay? So the rubber ball exerts a larger impulse because it bounces off. Okay? So, so that's the logic there. Okay? That cool? Everyone get that?
Yeah, that makes sense.
Okay. Okay. As long as we keep getting Dhruv's seal of approval, we can keep moving forward. Okay. So now we go on to the next one, and yeah, these 2-hour review sessions. It's quite the deal. So let's see. So this one is, and you can't read that. So on a frictionless track, a cart of mass m moving at speed v collides with an identical stationary cart. Okay, so I'll just draw this. Here's the stationary cart and it's identical. And there's another cart that's moving at speed v. And so this is your initial situation. And the final is that they stick together. So now they're stuck together and they're 2m. And so then they move at some new velocity, v final, right? So this is your final. And this time they're asking for the mechanical energy lost. So now there's only kinetic energy here, so it's delta Ke, is equal to what? And it's going to be, the change in kinetic energy must be negative, I guess. That's why there's a kinetic energy lost, okay? So, but it's, let's find that out. So we'll use conservation of linear momentum to find V sub final. Okay, so use this to find V sub final. And once you have V sub final, then the Ke final is, of course, 1/2 times the mass, which is 2m, V final squared, right? And then from that, we will compare that to Ke initial, which is 1/2 the mass mv squared, and the other guy is 0. Okay, so we can easily find the lost kinetic energy, right? So lost kinetic energy would simply be the initial kinetic energy, 1/2 mv squared, that's Ke initial, minus the KE final, because, you know, and where did it go? It just went into some deformation. And I mean, when things stick, they have to deform in order to stick. And so, you know, so the initial kinetic energy was larger, and the final is smaller. So you get, you know, and so there you have a 1/2 2m v final squared. So we just need to find out what v final is. So, and for that we're using conservation of linear momentum. Okay, and so what is the, you know, there? So what's the initial momentum? It's mv plus 0. The other guy was at rest. Final momentum, both the masses are now moving at this final velocity v sub f. We find from here that v sub f is v over 2. So we take this and we plonk in there. And so we find that the lost KE is equal to 1/2 mv squared minus 1/2 2m, and we have a v over 2 squared, so that's a v squared over 4. And so then you can simplify this, and what you will get is 1/4 mv squared. If you had done KE final minus K initial, this would have been a negative, which means that it was lost. So I look here and I get 1/4 mv squared. All right? Is that good? Any questions there? Okay. Number 10, I guess I should pick up the pace maybe a little bit. So number 10, you know, something moving in a straight line, but it has an angular momentum, right? Because even though it's moving in a straight line, relative to the origin, I mean, it's like it's, you know, moving past it, like that. So if you were standing at the origin, you'd have to turn your head to keep track of this object that started here and just kept moving like that, right? So so there is an angular momentum, and the angular momentum is defined as the position vector to the object. So that's this r cross the linear momentum, which of course is right here. That's this. So r cross p, right? And so, you know, the magnitude is simply the magnitude of r, magnitude of p, times the angle between the two. And what's the angle between the two? You can, you know, translate the p vector anywhere you want. So how about sticking it here? So there's p, and so the angle is this angle, right? The angle between the two vectors. Okay, so let's do this then. So the radius vector is, and they've given us, this is 2 and this is 3. Okay, so the radius is, you know, square root of 2 squared plus 3 squared. The momentum is the mass, which is 200 grams, times the velocity, which is 5 meters per second, and the sine of the angle. So this angle is theta, which means this angle is theta, and the sine would be opposite side 2 divided by the hypotenuse, which is, okay, and so this and this cancel, and so I'm left with 3 kg. Those are the units, kg meters squared per second. And so I see that now what's the direction though? And the direction is easy to see because there's your r vector and there's your p vector. And so, you know, the way I do it is I I use the right hand rule. There are many ways in which I guess you've been taught to use it. I kind of I stick my thumb perpendicular to the vector r and p, which means it could be pointing up or it could be pointing down, right? And so you can't see it when it's pointing down, but it could be pointing down, it could be pointing up. And which is the direction in which I hold my thumb such that I can rotate from the first vector to the second vector through the smaller angle, right? So here's the smaller angle between the two, r and p. I've drawn it, theta. And I find that if I hold my thumb like this, pointing up toward me, I can rotate from r toward p, okay? If I had my thumb pointing the other direction, then to rotate from r to p, I would have to go through the bigger angle, okay? So the thumb has to point up, and so it's pointing out of the page, okay? So out of page. So that's this one here, okay? Any questions on that?
Can you explain where you talked about the sign? Where did you?
So the right hand rule again. Yeah, I can definitely. Let's talk about that. That's an important question. So if you have
not the right hand rule. Like how did you know to use the sine function in your second equation?
Oh, okay. So the cross product, just as the dot product is the magnitude of A, magnitude of B cosine theta. Similarly, the cross product of the two vectors, the magnitude of the cross product is A times B sine theta. Okay, and the direction is given by the right hand rule. So because A cross B is a vector, A dot B is not a vector, it's a scalar, so there's the magnitude. The cross product, the vector product, gives you a vector whose magnitude is this guy with the sine function, and the direction is given by the right hand rule. Is that what you were asking?
Yeah, thank you.
Okay, good. Yeah, you're welcome. So yeah, there were two vectors, and I had to take the cross product, so that's why the sign came in. Okay. All right. So then we come to this guy. So this is a 400 Newton baby bear, a hungry baby bear, walks out on a hinged beam. The hinge is right here. And it's trying to get to these goodies, which are right here, hanging at the end. The beam is uniform, and it weighs 100 newtons. So right from the middle point, that's where the 100 Newton weight of the beam acts. And it's 4 meters long. So this distance from here to here is 4 meters. The goodies weigh 50 newtons. And the bear, we said, is 400 newtons. And he's out at this distance x. Okay. And then there is the horizontal and vertical forces at the hinge, because the beam presses into the wall, so there is a reaction force in the horizontal direction. Plus, this beam is trying to drag out, because of friction, it wants to fall down, or because of its weight, it wants to fall down. So this end is held up in some way, so there's a vertical force also. So those are the two forces at the hinge. The maximum, there's a tension force, and they're telling us that the maximum tension force is 400 newtons. Okay, so the question then is that how far out can the bear walk? What is this x that the bear walks out to? So, I want to use the you'll notice that I don't know much about the vertical force, horizontal force. The question is about the tension. So if I can avoid using these forces at all, I'd like to do that. So this entire system is in equilibrium, which means that the sum of the forces in the x direction must be zero, as also the forces in the y direction, as also the sum of the torques, tau is the symbol for torques, about any pivot axis. I mean, it's not rotating about any point or axis at all. So about any pivot axis, the sum of the torques should be zero. Choose your pivot axis wisely. Choose pivot axis. You can choose it anywhere you want. You can choose it right through the center of the beam like that, you know, going in and out of the page. You can choose it here. You can choose it here. You can choose it wherever you want. But if you choose it wisely, okay, to avoid having to use unknown, and not just unknown, but undesired. Like sometimes there's an unknown quantity that you want to find out. That's a desired unknown. But sometimes you don't really care. No one's asking about V or H. So to avoid having to use unknown, undesired forces, okay? So the best place to choose the pivot axis is to use this point right here. Use this as your pivot axis. Call this O, okay? So your pivot axis is going in and out of the page right through this point, okay? And the reason is that then the torques from the forces that pass through the pivot point, these torques have no lever arm. They have no capacity to rotate this, this beam about this pivot axis, okay? It's like trying to open or close a door by grabbing the edge of the door and then pulling or pushing on it. I mean, it's not a rotating motion at all. So, you know, by pulling the, I hope you got what I meant, but trying to pull it off its hinges or something, that doesn't rotate it. So, so we're going to use this, and we're going to use this as the pivot axis. And so you'll notice that the weight of the bear, the weight of the beam, and the goodies, they're all trying to make this beam go in the clockwise direction, right? They're trying to make this rotate about this pivot axis, right? They're trying to rotate this like this, clockwise. The only thing that's counteracting them is the tension, which is trying to make it go the other way, right? Counterclockwise. So, so about O, the clockwise torques from the weights of the bear, the beam, the goodies are all counteracted, must equal the counterclockwise torque from the tension. Okay? So that's the physics that we're going to use. And so now let's figure out what the torques are. So the clockwise torque due to the bear, the weight of the bear, that's 400. So that's right there. And the lever arm, or you know, the torque is always R cross F, right? So if let me just draw this thing here. So here's your beam, and here's the 400. So there's the pivot axis, 400. This distance is x. So it's R cross F. So there's the R is the x and the 400, right? So 400 times x, that's the torque from the bear's weight. Then there is the 100 Newton, and again it's R. R is the distance from the pivot axis to where the force is, R cross with the F. And of course the cross product, that's the sine of the angle between the R, right? And you'll notice that it's always 90 degrees, right? 90 degrees. So now in this case, the R is half length of the beam. The beam is 4 meters long, so that's 2 meters. Okay, so the torque in the clockwise direction, so it's adding to the torque from the bear. So it's 100 Newton times 2, right? And then finally, there's the goodies, which are 50 Newton, and the R, which is the vector right up to where the force is acting. And again, it's at 90 degrees, and this distance is 4 meters. So, and this torque, they're all acting in this direction. So this is going to be 50 times 4. So these are all the clockwise torques that are trying to make the bar go this way, and they must equal the counterclockwise torque from the tension. So what about the tension? Well, the tension is like that, right? And so you'll notice that the tension has two components. There is a tension, there's the vertical component, T, so if this is 30 degrees, that's T sine 30. And then there is the horizontal component, T cosine 30. And why did I talk about components? Because you'll notice that T cosine 30 passes right through the pivot axis. So it has no lever arm. It's just like these, the V force and the H force, they pass through the pivot axis. This passes through the pivot axis. There is no R when you go look for the R cross F to compute the torque. There is no R. It just passes right through it. Okay. On the other hand, the T sine 30, yes, that has an R. This is the R for the T sine 30, right there. There we go. Okay. And so that's 4 meters. Okay, that's the R, and cross F, which is T sine 30, and the 90 degrees gives you 1. If you tried to take a cross product between the R and the T cosine 30, you notice that it's a sine of 0, right? I mean, it's a sine of 180 rather. This is pointing out to the right, that's pointing out to the left. That's a sine of 180 degrees, and so that's 0 torque. That's why if you're passing right through the pivot axis, there is no lever arm, there is no R cross F. Okay, but the T sine 30 has a there's an R. Okay, and so that's 4 times T sine 30. So T sine 30 times 4. Okay, and this is the torque in that direction, and they must be equal for the torques to cancel. If you put in the maximum value for the tension, then you will get the maximum value for X, because if you maximize the right hand side, you maximize the left hand side. And this we know is 400 Newton. So now if you put in all that, X is the only thing that you have to solve for, and X works out to 1 meter. Was that a reasonable explanation? I tried to explain, the torque is, I tried this, and I also used sometimes in high school we're taught that it's a force times the lever arm of the force. Okay, and so this is of course RF sine theta. That's the magnitude of the torque. And this R sine theta is sometimes called the lever arm of the force. Okay, so the R times the sine theta is called the lever arm of the force. So the theta matters. Like just because this whole 4 meters is not everything. If the force is aligned with that, then the theta becomes 0 or 180, and the lever arm becomes 0. Okay, so any questions on this? And like I said, if there's something that doesn't sort of, if there's something that you feel a little not so comfortable about, then you can always ask me later. If the question doesn't sort of come to you right now. Okay, so then let's do number 12. So this is physics professor stands on a turntable and transforms himself into an orangutan, okay, monkey with long arms, holding 2 kg lead bricks in each outstretched hand. So once again, and then, you know, it's the figure skater problem, right? You, and of course, if it were face-to-face, we would have done this in class. But let's say, okay, so the initial position is where, you know, you have, okay, so yeah, so here's the head, and then the torso, the legs, the arms. He's a physics professor, so he has no biceps. It's like straight, spindly arms, easy to draw. But he's fit, symmetric at least. And so you've got your 2 kg lead bricks, okay, outstretched arms, and rotating. He's rotating initially with an angular speed of 6 radians per second. 6 radians per second is the initial omega. So this is a figure skater problem. Conservation of angular momentum is what we're going to use. Okay, and is there anything else? And then, you know, the moments of inertia are, we have to figure those out. We've been given that. The final situation is, so here's the final situation. And once again, so there, and this time he's, oh, and this distance was, yeah, so this distance is 2 meters, 2 meters, and now he's pulled it in. One meter. Okay, so he'll start going around faster, right? And you know, that's what happens when the figure skater pulls his or her arms in. Okay, so conservation of angular momentum. The initial angular momentum must equal final angular momentum if there were no external torques or anything acting, which means the angular momentum is, of course, moment of inertia times angular velocity, right? The initial moment of inertia from the torso, right? Because I think there's something, yeah, the moment of inertia of the orangutan plus 2. So everything here is 2 kg meter squared. So you've got the, you know, the moment of inertia for the orangutan plus the stool, that times the initial angular velocity, which is 6. But then you also have the moment of inertia of the bricks, and you know how to, you know, if you have a particle, its moment of inertia is just mr squared, right? So it's 2 kg times 2 squared, right? mr squared. And there's 2 of them, so there's another 2. I think that's a little confusing. So let's, basically what I'm doing here is I'm saying that the moment of inertia is the moment of inertia of the orangutan plus stool, plus there is the moment of inertia mr initial squared for each mass. So there's two of them, right? So there, and so that times omega initial, right? So that's where so there's that 2, there's the mass 2, and then there's the initial r squared 2. So all of this is your initial angular momentum. And then the final angular momentum is, this orangutan and the stool stayed the same. And again, you have the two masses, but instead of r sub I, now it's r sub f squared. And omega final, right? So let's just put in those values. So the moment of inertia, so this is 2 still. That's 2. The mass is still 2, but now the new radius is 1 squared omega final. So I just need to solve for omega final, and it works out to 18. It's speeded up, as you would have thought, radians per second. Okay. Is this good? Any questions? Okay, so what about this one? This one was a relatively straightforward one. Two masses, 2-point masses, each of mass m, separated. So here's one mass, there's another mass, and they're separated by a distance r. Okay, and there's a force between them. So the force, this is now where we're entering gravitation. So g times m divided by r squared. But now, I mean, what happens when you make it 2m and make this distance 2r and this 2m? So in that case, then the force becomes, g times 2m, when we're asked to compare the two forces, basically. So the new force, and this is over 2r squared. And you'll notice that the 2 squared is 4, cancels this, so you get back that. So actually this works out to be the same as this force. So when you double the masses and double the distance, it works out that you get the same force. So that wasn't too bad, right? So there is one problem here that I think I wanted to go over. Well, this one is easy too. What is the ratio of the force of the sun on the Earth to the force of the sun on Venus? And so, there's the, and as a confusing thing, I suppose, they do give you the radius of Earth and the radius of Venus also. They give you the distance from the sun to Venus and the distance from the sun to the Earth, but they also give you the radii of the planet. So I guess, that's the only thing that was tricky about this problem. So just remember that if this is the sun and this is the planet, then you got to use this distance, the radius from the sun to the planet. Use that, not the radius of the planet. That has nothing to do with anything. Okay, so that's the only thing to keep track of. And so this would be mass of sun, mass of Venus, radius, sun to Venus squared. And so a whole bunch of things cancel, this cancels with that. And so then you're just, you can simplify this. mass of Earth over r, radius from Sun to Earth squared, and you bring this up, so you get radius of Sun to Venus squared divided by mass. And so when you solve this out, you get 0.637, okay, which is that. So this was the only thing to keep track of. All right. Let me get to number 15, because I think that there's something about this problem which I did want to tell you. So in this case, you see, we're using gravitation now, because, you know, we're talking about distances that are far away enough from Earth. And so in this case, there's an object of mass 10 kg, and it's launched straight up from the surface of the Earth, okay? And this is actually a very bad diagram because the height h is, so you launch it up. I should draw the Earth like this. Actually, I should draw the Earth like this. It's huge, okay? Compared to this height h. I mean, you can see these are like thousands of kilometers. Meanwhile, the radius of the Earth, as they give us, is, you know, 1,000,000 meters. That's 10 to the 6 meters. These are all, oh, wait a minute, that's comparable. So actually, it wasn't a bad diagram that I had. So here's the Earth, okay? Okay, so radius of Earth. And we fling this object straight up, okay? So it's launched up with this velocity, and with an initial velocity of 5 kilometers per second. Okay, so v equals 5 kilometers per second. And they're asking how far up will it go? Okay, so it stops here somewhere. So if your v initial was 5 kilometers per second, v final is 0. And the question is that, you know, what is this height h that it went up to? And so it is really a conservation of energy problem. And so, you know, it's delta KE plus delta PE equals work done by non-conservative forces. There are no non-conservative forces here, it's all gravity. So whatever you lose in kinetic gets transferred to potential, all right? And so the change in kinetic energy is easy. It's, you know, the KE final is 0, and the initial is 1/2. The mass is 10 kg, and the V is 5,000 meters per second, right? So there's your delta KE. And I guess one sort of little exam trick I wanted to point out is that if you are forgetting how to use the gravitation formulas, you look at the answers, and you know there's quite a bit of difference between them. So I'm not saying this is the right way to do this, but let me just make clear that this is an approximate solution. Let's say you play dumb and you just say that the change in potential energy is mgh. Okay, so the mass is 10 kg, the g is 9.8, and you know, please understand that this is not really right. Okay, no, but still, let's just, from an exam point of view, if we were to do this, mg and then h, we're playing dumb, right? And then this is equal to 0, and you solve for h, and you find that you get 1.275 times 10 to the 6 meters, which is 1275 kilometers. And so you think that, okay, so this, the thing that's closest, I mean, the others are quite far away. This is kind of close. So if you had less time and you just needed to guess or something, then you can pick that. And indeed, that turns out to be the right answer if we do it correctly. So now we know the correct way of doing it. Correct solution. And that is that the PE initial and PE final, right? And so when you're using gravitation, then you've been taught that the PE initial is minus g times the mass of the Earth times the little mass divided by whatever the distance is from the center of the Earth. So there, and it's it's negative because it's defined relative to some zero which is at infinity, right? So there's your P initial. PE final is the same thing, but this time the distance is radius of Earth plus the h. And you'll notice that this potential energy is a smaller, it's negative of a smaller number. This is negative of a larger number, right? So the final potential energy is more positive than the initial potential energy. So even though these are both negative numbers, the final potential energy is less negative, it's more positive. So there is a gain in potential energy, just like there was a gain in potential energy mgh, So it does work out, it's just that it's a little more nuanced than when you used mgh, because there is no little g, it's changing as you go, so you have to use the correct formulas. Okay, so now I'm using the same idea like I did over there. The delta KE is still, this minus 1/2 10 5 times 10 cubed squared. The delta PE is PE final minus PE initial, which is minus gm of Earth times the mass divided by the final is right there, RE plus H, and negative of the negative P initial, so plus gm. Okay, so there. And so this works out to, you can take out the gm Earth mass of object out common, and you're left with a 1 over R sub E minus a 1 over R sub E plus H. Okay, and so we can put in the, and well, I mean, this you can simplify, I suppose. The denominator is R sub E plus H, and you get an R sub E plus H minus R sub E. Okay, so this is G M sub E M H divided by R sub E plus H. Okay, so this is your change in potential energy. Okay, and so now you can, and we know all the values here except for H. H is the only unknown. So let's put this into that conservation of mechanical energy formula. So the change in kinetic energy minus 1/2 10 5,000 squared plus the change in potential energy, which is this thing right here. So what's big G? Big G is a constant, 6.67 times 10 minus 11 in SI units. The mass of the Earth is given as 5.98 times 10 to the 24. The mass of the little object is 10 kg. H divided by the radius of the Earth. Radius of the Earth is 6.37 times 10 to the 6 times 6.37 times 10 to the 6 plus H. So all of this is equal to 0. Okay, so you can, so this would be an equation in H, a linear equation in H, if you just multiply across by the denominator. Okay, and so you can solve. It's a linear equation in H. So solve, okay, and what you find is that H is equal to 1589 kilometers, which is very close to this answer. So the 1571, I think, is a bit of a mistake, okay? But it's close enough to the 1589, so you can pick that, okay? Any questions on this, what we did here? So, please don't, I mean, you can use this as a quick estimate or a guesstimate, but, please remember that the little g is not constant everywhere. It's not 9.8, so it will give you a wrong answer. As you can see, but it's reasonably close. Like, I mean, but if the examiners, if the professors were mean, which they can be, they can put in a value calculated from this wrong calculation in there as well. So it's better to do it the right way. Any questions on this one?
Why is the potential energy at the top negative?
Yeah, so the potential energy at the top is negative because the zero was so defined in this case. The zero was defined way out at infinity. And so all the potential energies everywhere are actually negative, but that's okay because what matters is the change in potential energy. And you'll notice that as you move up or away from the Earth, you expect the change in potential energy to be positive. And that is indeed the case. You see how the potential energy close to the Earth is negative, and it's a larger negative number than the potential energy at that height h, where you see the denominator is now larger because there's a plus h. So this is negative, but it's a smaller negative number. This is a larger negative number. So the change is a positive. And in the end, that's all that really matters. The change in potential energy is what we observe in real life. Where we define our zero is of not much consequence or any consequence at all. So the change is still positive, just like MGH, the change was positive when you went up. The change is still positive. Does that answer your question?
Yeah, thank you.
Okay, great. Thank you. All right, so now we're down to our last four problems. Let's look at them. So let's see. Number 16 is a similar one on gravitation. A group of astronauts land on an unknown planet of radius 5 times 10 to the 6 meters, and then on that planet they drop a test mass. Okay, so there's the initial and then they drop it by 1 meter. So here's the final. And there. Okay. And it takes 0.5 seconds, they notice, to hit the ground. And so the question is that what is the mass of this unknown planet? And so okay. So we don't really know, what the acceleration is. Like otherwise, I would have used any of the kinematic equations, right? I mean, the 1D kinematic equations is what I'd like to use. Well, the thing is, no, not really. I mean, the 1D kinematic equations don't really tell me the mass of the unknown planet. The mass of the unknown planet will only come into the potential energy, just like the problem we were just doing. So if I want the mass of the unknown planet, mass of unknown planet appears in the change in potential energy formula. So I should use conservation of mechanical energy to try and find that. And so it's a change in potential, change in kinetic, work done by non-conservative. There are no non-conservative forces. What do I do? So, we're on the planet. The planet, of course, is, something like this. So there is a radius to it. And so the change in potential energy, well, the final potential energy is negative g times the mass of the planet, right? Mass of the planet times the little test mass, and we don't know the test mass. They've not given it to us, which means it'll probably cancel. So there it is. We'll put it in right now. And the final potential energy is, where it's just the distance r away from wherever the radius, right? So radius of the planet. That's the final potential energy. This right here is the potential energy final. And then I need the negative of the potential energy initial, minus potential energy initial. Well, what is the, okay, so here's the minus. And then what's the potential energy initial? It's minus g mass of planet, mass of test mass, divided by the radius of the planet plus the height. This height is 1 meter. Okay, and so that's the change in potential energy. And of course, when it fell down, just before hitting the ground, it had some velocity. So there's a kinetic energy that it has. So there is the kinetic energy, it gains kinetic energy. That's where the potential energy went. So there's a 1/2 the test mass and whatever this v is at the final, just before it hit the ground. And the initial was 0, right? Because it was dropped from rest. And so all this is equal to 0. So you notice that the masses, these test masses, they cancel everywhere. Okay, because it's in every term. And then the other stuff, I guess we just have to simplify it once more. So here, you have the g times the mass of the planet. And this is a positive term, negative, negative, right? So we have a 1 over radius, this plus height, negative of 1 over the radius of the planet, plus 1/2 vf squared equals 0. And so let me take this over to the right-hand side, because this is a negative thing, because this is a smaller, the denominator here is larger, so this is going to be a smaller thing than that. So then I would get 1/2 vf squared, which is still on the left-hand side, is equal to, this goes over to the other side, and so I have a 1 over rp minus a 1 over the radius of the planet plus height. So, so therefore the v final squared is equal to 2 times this. And if I want to simplify this, then this is the denominator, and then this minus that just gives you an h. And so the point here being that I can find the mass of the planet if I know the velocity just before it hits the ground. And that I can use kinematic equations, to find v sub f. And once I know v sub f, I can plonk that in here and find out the mass of the planet, because everything else is known. So this is not bad at all. If I want to find the velocity just before it hits the ground, I don't know the acceleration. All the 1D kinematic equations use acceleration. I don't have the acceleration, so I'll have to sort of get at it in 2 steps. So the first is to say v final equals v initial plus the acceleration times delta t, right? Drop from rest, so that's 0. So v final is equal to acceleration, and delta t is 0.5. But I still need to know the acceleration. So I need to look at, they've given me the distance, you see, so I can use delta, and let's just say this is positive. So I'll use delta y equals v initial times delta t plus 1/2 acceleration times delta t squared, right? The initial velocity is 0. Delta y is -1 because it fell down. 1/2 the acceleration, and the delta t is 0.5, so squared. So from here, I can find that the acceleration is -8 meters per second squared. So if I take this and plonk it, plonk here. Okay, so I can find v final. Therefore, v final is 8 times 0.5, so that's -8 times 0.5 is -4 meters per second. So it's pointing down, that's why the minus, and 4 meters per second. So I just need to then bring this in here, so -4 squared, equals, and then everything is known here, everything. This is 1 meter, the radius of the planet is given, everything is known. So I can solve for mass of planet. Okay, so everything known except mass of the planet. So mass of the planet then works out to be 3 times 10 to the 24 kg. Okay. Any questions about that? Now I understand that we're at 10 o'clock, and so we've sort of overshot. I will still stay and do the last 3 problems, 17, 18, 19, last 4 problems. You are most welcome to stay, obviously. I will be recording this. I hope, I should check, but I hope it's been recording all this while, otherwise I'll be really sore. And I will be posting that recording, so you have the choice of 2 hours is a lot. I mean, to take just one person going on and on. But I guess we're in exam mode, so we have some superpowers at this point to be able to put up with all this. So I'm just going to keep charging forward, okay? So now let's look at number 17, and this is about rotational motion. Marble rolling along a horizontal floor, okay? And then it comes to a 35-degree incline. So it rolls up, and so here's the marble initially, right? And it's rolling and translating both, right? And then it moves up, it comes to this incline and it moves up, and the kinetic energy gets transferred to potential. And so, I mean, it's going to roll up, and at some point it's going to roll back. It's going to stop. So this is the stopping point right there. And this, of course, is the starting. So it raises itself by a certain height. And the question is how far up the incline. So really they're asking for, this distance. How far up there. Actually, it's this distance. Okay, so so it's this distance that they want. All right. So we can do this. Once again, it is conservation of mechanical energy. Change in kinetic, change in potential equals work done by non-conservative forces. And this time there's two kinds of kinetic. There's the delta KE translational, plus there's the delta KE rotational, right? T and R. There is clearly a change in potential energy. The work done by non-conservative forces is zero because even though there is friction, you cannot roll unless there is friction, because even though there is friction, this friction does no work if only pure rolling occurs. So as long as the wheel does not slide and there's no rubbing going on, if only pure rolling occurs, then no work is done. And I can talk more about that if anyone needs to, but I mean, that's really the idea. So for this reason, the work done by non-conservative forces is zero. Okay, so there's translation, there's rotation, and then there is the change in potential energy, which is just, it raises itself, the mass times the g times the h, and it's a plus because it raises itself. All right, so what's the change in translational? Well, in the end, it's zero, and in the beginning, it's 1/2 mv squared. What about the rotational? Well, at the end, it's zero, and in the beginning, it's minus 1/2 I omega squared, right? That's your rotational kinetic energy. What's the moment of inertia? What is this? So it's 1/2. The moment of inertia is, you have to treat it like an object that's rotating about an axis going through its center, right there. And so the moment of inertia is 2/5 mass times radius squared. And you'll notice that they did not give us the radius of the marble, but I'm not panicked because that means that it's going to cancel. Okay, and what about omega? What's the omega? Well, just remember that this velocity at which this wheel moves forward is related to the omega. If this is the radius r, then v is equal to r times omega. Like, I mean, the rotational motion and the linear motion are related. They have a relation that they must satisfy. And so the omega is v squared over r squared. And so you notice that the radius cancels. So putting this together, all of this together, I have a minus 1/2 mv squared and a minus, and this also cancels, a minus 1/5. I've been writing the m differently everywhere. V squared, right? So that's your change in kinetic energy, total. And then you have the mgh is equal to 0. So okay, so I can now stick in the, let me find out h. And once I have h, then it's clear that h is equal to d sine 35. So once I know h, I can find d. So all right, so in this case, I have a minus half minus 1/5. So anyway, so mgh equals 1/2 and 1/5 is 7/10, I think. 1/2 plus 1/5. 1/2 plus 1/5. And the mass, the v squared is 7 squared, so that's a 49. And so the h, well, the m cancels, and then the g, I divide it by that, and so there. And this works out to 3.5 meters, which means that the D is h over sine 35. And so this works out to 6.1 meters. So there. Okay. So any questions on that, guys? Is good?
Is that 49 a given? Where'd you get that 49?
Yeah, sorry. So 49 is the v squared, which is 7 squared. 7 meters per second. Yeah.
Okay. Thank you.
Yeah, you're welcome. Okay, so then we zoom on to number 18. Number 18 is this, I'm reading out the question. Thin uniform rod, this is a rotational motion, and they've given you the moments of inertia and everything. Thin uniform rod of mass 400 grams, so that's 0.4 kg, is rotating clockwise about its center. So the pivot axis is right there, center. Determine the constant torque that will bring the rod to rest in exactly 10 rotations. Okay, so it's rotating. All right, so what do we do? What we want to do is, what we've been given is the initial angular speed, omega sub I. Now that's revolutions per minute, so you have to convert it to radians per second. So that's 20 times each revolution is 2 pi radians, and per minute, so now I've got the radians on the top, and per minute, so that's 60 seconds. Okay, so there you go, that's your conversion into radians per second. The omega final is 0 because you're bringing it to rest. In how much time, like what's the total displacement over which you bring it to rest? 10 rotations, so 10 times 2 pi radians. And so we need to find the torque that will bring it to rest. Now, the torque is the moment of inertia times alpha, right? That's the direct rotational analog of F equals ma, right? So m, the rotational analog for force is torque, for the mass is moment of inertia, for acceleration a is alpha, the angular acceleration. Okay, this is the angular acceleration. Okay, so if I know alpha, then I can find out, I know what the moment of inertia is. It's basically the moment of inertia is just, it's a rod rotating about its center. So there, that's the formula that I should use, right? So this is 1/12, and mass times L squared. So the mass is 0.4 kg, and the length is 75 centimeters, so that's 0.75 meters squared. So there's your I, and the alpha, well, we don't know what it is, but if I knew alpha, then I can find out the torque. So to find alpha, use the rotational kinematic equations. Rotational kinematics. And what that means is that you know the 1D kinematic equations, like for example, those three equations, right, that we learned in the beginning, and one of them is Vf squared equals Vi squared plus 2 acceleration times delta x, right? And the rotational analog for this is omega final squared equals omega initial squared plus 2, instead of acceleration you have alpha, instead of delta x you have delta theta. And the reason I zeroed in on this equation is because this does not have the time in it. And notice that we were not given the time, we were given the distance, 10 rotations. Okay, so we were given kind of the rotational equivalent of delta x. So that's why I didn't want to go use one of the equations which had time. And so, you know, when I use this, then omega final is 0. Omega initial is, I just wrote it up there. So it's 20 times 2 pi over 60 squared plus 2 times alpha, and then delta theta I wrote here is 20 pi. So from here I can solve for alpha. And what I find is that alpha is minus pi over 90 radian per second squared. So I'm just going to use this and plonk it in here, and I get the torque. Okay, so when I plonk in there, I find that the torque, the retarding torque, and that's why it's a negative. Well, it's just, you know, you plonk that in, and so this works out to 6.54 times 10 to the negative 4 Newton meter. Okay, so I look up here and I see 2 of them. And obviously, the torque that's going to stop this must be going in the opposite direction. So that's a counterclockwise. So that's this guy. Does that make sense? Any questions there? This is good? All right, so we're finally now down to the last 2 questions. Mercifully, number 19 is quite easy because, you know, they give you they have a particle moving along the y-axis. Potential energy is 7y cubed joules, where y is in meters. And then they're asking for the magnitude of the y component of the force. Well, that's easy because the force is given by, and I have to put the magnitude of it, but the force is the negative gradient of the potential, and if I'm looking for the force in the y direction, it's the gradient in the y direction, like that. And the magnitude sign, so I'll put that in. Okay, and so this is equal to negative, and what's the gradient of 7y cubed? Well, it's just 21y squared. And they are telling what is they're asking what's the magnitude of the y component of the force at y equals 2 meters. So I'm supposed to do this at y equals 2. So this would be magnitude minus 21 and then 4. And so that's 84 Newton. Okay, so this was, I just used the definition, 3 lines, that's a definition. Any questions there? How many brave hearts are left? Well, I'll see after. Okay, so there's that, and then the last one. The last one here was there was one thing that was a little tricky about it. 6 dogs, okay, 6 dogs pull a 2-person sled. Okay, so it's like here, and so there's the sled. Okay, and there's 2 people in it. I don't have great drawing skills. And it's pulled by 6 dogs. These are the faces of the dogs. I'm getting a bit loopy after 6 hours, 2 hours of doing this. And these are 6 dogs. So it's a six-faced dog. The rope is coming right out of its butt, okay, and it's pulling it. And so the question says total mass of 220 kg. So this whole thing is 220 kg, and the coefficient of kinetic friction between the sled and the snow, so mu k is 0.08. The sled accelerates at 0.75 meters per second squared. So the acceleration is until it reaches a cruising speed. So there's a cruising speed now. V equals 12 kilometer per hour. Let's convert that to meters per second. So 12,000 meters, hour is 60 minutes, 60 seconds. So that's meters per second. Okay. And here's the slightly tricky part. What is the team's power output during the cruising phase? Not building up to the cruising phase, but during the cruising phase. So what that means is that once it reaches the cruising speed, then what's the power output? So that's important. Like I'm gonna write that out. Power output during the cruising phase. And so the point is that during the cruising phase, the velocity is constant. And it's this object up there, right? To 12,000 divided, so that works out to 12,000 over 36. So this works out to 3.33 meters per second. So it turns out that how you got there doesn't matter. So this actually is irrelevant. We don't really use that. Okay, and so what is the power output? Well, the power output is defined as the rate of doing work okay, and this is well, so what is the work? It is the force dotted with the displacement, but then the rate of doing work means that in how much you did this work over some time. And so in the one-dimensional case, the dot product, I mean the force and the delta x are all in the same direction. So F delta x over delta t. And if the force is constant, then the only thing that is changing with delta t is the displacement. So it's F times delta x over delta t. And so that looks like a force times velocity, right? So the power output is the rate of doing work by the team, right? The team's power output. So team's power output is rate of doing work by the dogs. So this force here is the F by the dogs, right? And so in the cruising phase, here's the thing, and the force by the dogs is pulling it along. But you do have the frictional force in the other direction, and the net effect is that it's moving at a constant velocity, cruising, right? So that means that F dogs is equal to the frictional force, okay? Because the acceleration is 0 in the cruising phase. And so what is the frictional force? The frictional force, well, there is the normal force, which is mu k mg. Oh, sorry, normal force is mg, sorry. And because, there's mg down, and the normal force and mg should cancel. And of course, the frictional force is mu k, the normal force, which is mu sub k times mg. So here you go. So the frictional force, this is mu sub k mg. Okay. So therefore the power output is equal to the force by the dogs, which is mu sub k mg, and then the velocity v. And so if we put in those values, 0.08, put in the mass, 220, put in g, 9.8, put in the velocity there, and you come up with 575 joules per second, or watts. So that's your answer right there. Okay. So that then concludes all the 20 questions for exam 3. We kind of overshot. I wasn't expecting this has been a 2-hour 20-minute sort of review session, and you know, if you have any questions, let me stop the recording, I suppose.